In today's video, I will show you how to determine the ship's underkeel clearance, also known as UKC. Let us start. Underkeel clearance, or what we call UKC, is the vertical distance between the vessel's keel and the seabed. In calculating the ship's UKC, always follow the company policies and guidelines. This is the form that I used in my previous company to determine the ship's UKC. I will use this procedure in today's video. This procedure may differ if you are in a different company. Just check the company SMS or Safety Management System manual for the procedure and minimum UKC requirements. To find the UKC, we need the depth. This refers to the depth of the water. Then the height of tide, the vessel's draft, the ship's squat, swell, and the category of zone of confidence or CATSOC. The company policy requires that the minimum UKC should be greater than 10% of the ship's draft throughout the transit, starting with the depth of the water. The numbers that you can see in this chart represent the depth measurements that indicate the water depth in meters at specific locations. For this specific location, the depth of the water is 23 meters, here is 18.1 meters, and in this location, the depth of the water is 12.3 meters. Let us assume that you are making a passage plan and your ship will pass through TSS south of Gedser. Upon checking, 12.3 meters will be the lowest depth sounding that your ship will be passing through the entire transit. This is our recommended lane because this lane is a deep water route and intended for deep draft vessel. Here it's stated that vessel with a draft of 16.50 meters and greater are considered deep draft. In some TSS with deep water route, vessels with draft 15 meters and greater will be considered deep draft vessel. Let us assume that our vessel has a lesser draft, so this is the recommended lane. Since 12.3 meters is the lowest depth, we will calculate our UKC using this depth. The depth soundings that you can see in the chart are based on the lowest astronomical tide, or LAT. Lowest astronomical tide refers to the lowest level that astronomical tides are predicted to reach under average meteorological conditions over an extended period. It is essentially the lowest tide level that can be expected due to the gravitational influences. It means that the 12.3 meters depth sounding will increase due to high tide, and it can be 13 meters or 14 meters or more depending on the height of the tide, which can be found in the tidal tables. For now, we will leave this height of tide blank. We will see if the ship can pass a 12.3 meters water depth without relying on the high tide to comply with the minimum UKC requirements. Let us proceed to the vessel's draft. We have the different aspects of a ship's draft, the static draft and the dynamic draft. Static draft refers to the draft of a ship when it is stationary, at rest in the water, or dead in the water. Dynamic draft, on the other hand, takes into account the dynamic effects on the draft of a ship when it is in motion. It includes factors such as the influence of waves, ship speed, squat, and the ship's response to sea conditions. The draft that we will be using in this calculation is the static draft, and we will take the ship's deepest draft. Let us assume that the ship's deepest static draft is 7.50 meters. The value of the ship's draft, squat, swell, and zone of confidence will be subtracted from the depth of the water to find the ship's UKC. The only value that will be added from depth is the height of the tide. Next, we will proceed to the ship's squat. To determine the squat, we can use a squat calculation table or software, or we can calculate it manually. In this video, we will calculate the squat manually. I have made a separate video on how to calculate the ship squat. Kindly check the link in the description. The formula to calculate the ship squat is: squat in open waters is equal to the block coefficient, times the squared of the ship's speed relative to the water, divided by 100, the answer will be in meters. For confined waters, the formula is: squat in confined waters is equal to the block coefficient, times the squared of the ship's speed relative to the water, divided by 100, times 2. Where CB is the ship's block coefficient. V stands for the ship's speed relative to the water. Let us assume that the ship's trim is 1.00 meter by the stern, her speed is 11 knots, and her block coefficient at a given draft is 0.8450. Let us solve this example using these formulas. For squat in open waters, it is equal to the block coefficient, which is 0.8450, times 11 squared, which is the ship's speed relative to the water, divided by 100. The squat in open waters is 1.02 meters. For the squat in confined waters, we will just multiply the squat in open waters by 2. So we have 1.02 meters times 2. The squat in confined waters is 2.04 meters. Since the ship is trimmed by the stern at her static draft, the squat will take place on the aft and there will be an increase in the ship's trim aft due to the squat. An increase in the trim will be a decrease in the ship's underkeel clearance. That is why we will subtract the ship's squat from the depth of the water. Since we will be passing shallow water, we will take the value of squat in confined waters. So the ship's squat is 2.04 meters. Kindly check the link in the description on how to calculate the ship's squat manually. That video shows how to extract the value of the block coefficient at a given draft using a hydrostatic table. Next is the swell. We can determine the value of the swell in that particular area through the weather forecast or weather routing. Let us assume that the information given from the weather routing in that particular area, the swell is 1 meter. So we will subtract 1 meter from the depth of the water. Next is the category of zone of confidence known as CATSOC. The zone of confidence is composed of 6 categories, A1, A2, B, C, D, and U, with their corresponding symbols and the accuracy in position and depth. Starting with category A1, which is the most accurate, down to category U, which is unassessed. I will not go deeper into the discussion of CATSOC. Let us focus on the depth accuracy since we are calculating the ship's UKC during our passage planning. This is what you can see in the ECDIS monitor if we activate the zone of confidence. In this ENC, the symbols that look like an inverted triangle have 6 stars inside. The category of zone of confidence is A1, in which the depth accuracy is equal to 0.50 meter plus 1% of the depth. Let us find the accuracy of 70 meters depth sounding in this chart. First, we will determine the 1% of 70 meters, so 70 meters times 0.01 is equal to 0.70 meter. Then, add 0.50 and 0.70 meter, the accuracy is 1.20 meters, this value is the zone of confidence margin. This value will be subtracted from the depth to find the UKC. If we subtract 1.20 meters from 70 meters depth sounding, we will assume that the actual depth is 68.8 meters, not 70 meters, following the zone of confidence margin. Let us check another chart. As you can see in this ENC, we have different categories. This area has only 2 stars, so it belongs to category D. Here we have 3 stars, this is category C, and we have also category B with 4 stars. Let us find the depth accuracy of this 38 meters depth sounding in which the zone of confidence belongs to category C with only 3 stars. To find the depth accuracy, it is equal to 2.0 meters plus 5% of the depth. We have 38 meters times 5% is 1.9 meters, plus 2 meters, the margin is 3.9 meters. This is now the CATSOC value which will be subtracted to the depth to find the UKC. If we subtract this from 38 meters, we will assume that the actual depth is 34.1 meters instead of 38 meters, following the zone of confidence margin. This is how we compute the depth accuracy using the CATSOC in our ECDIS. In this chart, in which our ship will pass a 12.3 meters depth sounding, let us assume that the zone of confidence is category A2. This may differ from the actual ENC you are using on board. To calculate the depth accuracy, first, we will determine the 2% of 12.3 meters, so we will multiply it by 0.02, and that is equal to 0.25 meter. Next, we will add 1.0 meter, the accuracy is 1.25 meters. This is now the value of our catsock, which also be subtracted from the depth. We will now subtract the vessel's draft, squat, swell, and zone of confidence from the depth of the water. The ship's UKC when passing 12.3 meters depth at a speed of 11 knots is 0.51 meter. To find the minimum UKC, let us multiply the ship's draft, which is 7.50 meters, by 10%. The minimum UKC should be greater than 0.75 meter. In this case, we did not meet the minimum UKC requirement as stated in the company policy. The big question is there any way that we can still pass the intended traffic lane without using the traffic lane intended for deep draft vessels? Yes, there are ways. The primary option is to wait for the high tide. Check the height of the tide using your tidal tables. You can use a hard copy or a digital form depending on the availability on board. Let us assume that the height of tide is 2.5 meters during high tide. By adding the height of tide, the ship's UKC now is 3.01 meters, which is 4 times greater than the required minimum UKC. The next option is to reduce the ship's speed by 1/2. Reducing the speed by 50%, the ship's sinkage due to squat is reduced by 1/4 or 25%. The 25% of the ship's squat, which is 2.04 meters, is 0.51 meter. Subtracting 0.51 meter to the ship's squat, the remaining squat is 1.53 meters. By reducing the ship's speed to 5.5 knots, the new squat is 1.53 meters and the ship's UKC is 1.02 meters. In this method, we can still pass a 12.3 meters depth sounding without waiting for the high tide and without violating the company policy for the minimum UKC requirements. In this example, we assume that the water density throughout the voyage is salt water. If there is a change in water density when passing shallow water, it should be considered in calculating the ship's UKC, especially when passing from higher density to lower water density, because the effect will be an increase in ship's draft due to sinkage.